Okay, assignment 1, unit 1, assignment 2, calc AB. So you should have tried these problems already, and I checked them. Solutions were posted, and I guess I'll go over these real quick, and then you can make corrections and figure out what you're not understanding. So the first are the following numbers integer, rational, or irrational? And they could be more than one, by the way, because integers are rational numbers, right? So it could be integer and rational. So this is rational. It can be written as a fraction. This is rational because you can write 0 as a fraction, but it's also an integer. Okay, all integers are rational. So both those answers. This is 4, which is an integer. So it's an integer in disguise. It's equal to integer, but it is also rational. It can be written as a fraction. 0.7 is the same as 7/10. So that's rational, but it is not an integer. Number 5, with the repeating, 0.8111111, we know is a rational number. It's not an integer. Square root of 2, irrational. It's non-terminating and does not have a pattern. Number 7, e is irrational. The natural number e is irrational. Pi, irrational. 9 to the 1/2 is the same as the square root of 9, which is 3. So it's an integer and it is rational. Square root of 3 raised to the 4th power is the same as 3 squared is 9. So that is rational and an integer. Square root of 3 by itself would be irrational, but this seems to have a pattern. Like I see a pattern, but it's not a repeating decimal pattern. It's not the same repeating decimal, so this is irrational. You cannot write this as a fraction. Even if there's a pattern, it's got to be the same group of numbers being repeated. Any size group of numbers being repeated, but can't add to it as you go. These ones, we're using that trick to convert them to fractions. And even if you know what the answer is, you should be practicing it, because in your next test, I'm going to require you to show this particular kind of work. So what we do is we set it equal to n. We multiply both sides by 10 raised to the number of repeating decimals. So there's only one repeating decimal here, so we're going to multiply both sides by 10. So we're going to get 10n equals 3.3 repeating. I'm going to subtract n. And we're going to get 9n equals 3 and n equals 1/3. So that's the way you're going to show your work. 13, this equals n. We're going to multiply both sides by 100 because there's 2 repeating digits. And that's going to move the decimal place over 2 spots to the right. And then when we subtract n, it should line up just right. You want to line up the decimals so the repeating parts cancel each other out, and you get 99n equals 36. You divide both sides by 99. We could reduce this. We could take a 3 at least out of both of them. And then we could take a 3 out of both of those. And that the answer is 4/11. Number 14, if it just has zeros forever, then we could just write it as 36/10ths. You don't really need the trick for repeating zeros because that's the same as just no zero. So then that'd be 9/25. 15, we're going to multiply both sides by 1,000, 10 to the 3rd, because there's three repeating digits. So that's going to give you 205. It's going to move this over 3 spots, but then you're going to keep getting 205 repeating, and we subtract n, and we get 999n equals 205. And I think that's it. I don't think we reduce that. You could try some tricks. Does 9 go in? Well, 9 goes in that for sure. If you add all the digits, 2, 0, and 5 is 7. Does 9 go to 7? Nope. 3 doesn't go in. Nope. 5 doesn't go into both of these. They're not even. So this one looks a lot like the last one, but there's only 2 repeating digits. So we're going to multiply both sides by 100. And then that's going to give you 20.5. Oh, and you could write the repeating like that, but we want it to be like this so that it lines up. When we subtract n, we want to be able to subtract it so the repeating parts cancel each other out. Now this is one of those ones that has a decimal, 20.3, and that is not cool for final answers. Okay, I will take off credit on your next test if you give me a rational number with decimals in the top or bottom. So we're going to multiply top and bottom by 10 is the quick trick for getting rid of the decimal, and then you might have to reduce it. So this one, we're going to multiply both sides by 10 because there's only one repeating decimal. So it's going to be 1.233 repeating. You want the repeating 3 to be there so that when you subtract n, that the repeating part of the original n lines up nicely. Okay, so then we have 9n equals 1.11. And then we divide both sides by 9. And then that's going to be 111 over 900, which we could divide a 3 out of the top and bottom. It would be 37 over 300. So that's how we do repeating decimals. You're going to have a few of those on your next test. You're allowed to use a calculator for this part to just make comparisons. It says Ryan Papyrus, 1650 BC, says that the area of a circle can be found by a equals 8/9 diameter squared. What approximation of pi were they using? Well, if you want to figure out what they're using for pi, let's compare it to our formula for our circle, for an exact circle. And this is an approximation. It should be pi r squared, and theirs is going to be close. So what we could do is we could change their diameter, the radius over 2, right? And then the whole thing is being squared, which means it's going to be 4/9 squared and then r squared. So that must be what they're using for pi. They're using approximately 4/9 squared, or 1680 over 81. Oh, hold on, I messed up. The diameter is 2 radiuses, so that's going to be actually 16 over 9 squared. 16, so it's going to be 256 over 81. So I screwed that. Okay, but that's our approximation for pi. And so these are some other ones, and you can put that, it says which of these is the most accurate. So what we could do is use our calculator's version of pi, which we're assuming is accurate to what they display, and then we can compare these other ones next to it. So we could, we can compare 333 divided by 106, and it equals, so I mean, if you want, you could write down, okay, well, this is 3.141592654, and then this one comes out to 3.141509434, and you can say, well, where does it first go away from it? And it's right here. And so we could do that for each of these. 355 divided by 113, 3.141599292. And so it first goes away from it right here, it looks like. So that one's better than the last one. So these are all different estimates that civilizations and mathematicians were coming up with for pi. And some of them came up with better ones. So 223, so you could write that down. 3.140845507, and that one is accurate until right here. 22 over 7 is 3.142857143. So that one's accurate to not that good right there. So Archimedes had a couple, and they both were about as good as each other. This one's a little more complicated, but we could type that in. 63 divided by 25. We got to make sure you have the correct grouping symbol. So we definitely need grouping symbols around the whole second fraction and around the denominator, the numerator of it. So close the square root, close the numerator, divided by, you need parentheses around the denominator, 7 plus 15, square root of 5, close, close, close. And I think I entered something in wrong because that doesn't look good at all. Let's see. What did I? I don't know. Lost my shoot. So what this one should come out to, I believe, is 3.141592654. That one's accurate all the way to, looks like 4 compared to our pi. So this one is the best. I don't know. I typed it in my calculator wrong. So on the back, we had a little bit of algebra review, kind of algebra 1 review. And we did a couple of these in class, so I'm not going to redo those. We did 20 and 23. And I wanted you to just try and do them the way that you remember doing them. Now, linear ones are easy because then you just isolate the single variable, and it comes out correct. I did want you to write your answers in interval notation. So that would be the same as -5 to positive infinity. And we always put a parenthesis on infinity. And we put a parenthesis on any not equal to boundary, but this one's already equals to, so it's going to have a bracket. So you need to get used to that notation because we use it a lot this year. It's very common on the College Board's advanced placement exam for calculus. This one I started doing, I said this was not a good approach. You probably want to do this. Find these, and then the way that, there's two ways that you may have done it. You might have said, okay, well, let's test a value in each chunk. So test x equals 4. Is 4 squared greater than or equal 9? Yes, it is. And then you could test a value here, x equals 0. It's false. Test a value here, x equals like -4. It's true. And so those are your answers. So you have a picture of your answers, and then you could write your answer. You could say, okay, well, it's the way you would have written it before is you say x is less than or equal to -3, or, and that's a key word, x is greater than or equal to +3. Okay. But now we're going to write it as this, -infinity, comma, -3. Parenthesis, this is going to be a bracket because it's a solid dot, or bracket 3 to +infinity. So this is the new way we're going to try and write our answers most of the time. Now the other way you could have done it, which I've shown you up here, is by using a graph and say, okay, well, this is like y right here, and this is a parabola opens upwards, and y is less than it, so we need to shade down below it, and then wherever that intersects the x-axis, those are our answers. I like that approach because I feel like it just makes sense. It's quick. I think it's quick. I think it makes more sense than just checking a bunch of numbers over and over again. Now this one is linear, but it's already compound. So you want to get x by itself. Whatever you do in the middle, you got to do the right and the left, right? And then you want to solve. So you want to do reverse order of operations. You want to get rid of addition and subtraction first, then multiplication and division. That's generally the quickest, best way to go. And so then that's your answer from last year. But now this year, we're going to write it as 3, 6 brackets. Okay. This one, 6x squared plus 7x minus 20 less than 0. So in general, in polynomial inequalities, you're going to move everything to one side equals 0. Try and factor it. GCF first. There is no GCF. So then you got to find a pair of numbers. It's either 6x and 1x, or it's going to be 3x and 2x, right? You're going to still have the less than 0. And then it's got to be pair numbers that multiply together to get negative 20, but then can be combined with the first terms to get 7. So if we try, the negative 1 here and 20 there, then that would be 14. If we do negative 2 here, that's going to be 12. And 10, that's going to be 2. So I don't think that one's going to work. So here, if we do 1 and 20, that's way big. That's 58. If we do 2 and 10, that's 26. If we do 4 and 5, that would be 15. Positive 15 minus 8 is 7x. Okay, so then x equals 4/3. We set each of these equal to 0. It's called the zero product property. X equals negative 5 halves. Set equals 0. Subtract 5. Divide by 2. And then you could set up your number line. Now these are going to be open dots. You want to go left to right, smallest to biggest on number line. Negatives are on the left, positives are on the right. Now you could test each region like we talked about, or you could be like, this is a parabola that opens upwards because the leading term is positive, and y has to be greater than, so we're going to shade up, and then here are the answers. So the answer is in interval notation, or negative 5 halves to 4/3. Now we're going to put parentheses this time because they're open dots, because they're not included in the solution. So, all right. Hopefully you understand the homework now, and I'm all ready for today's lesson.